Hey, hello everyone. So, welcome to my talk on optimizing Ruby, building an always-on production profiler, and the third talk at RubyKaigi this year about profiling, which I am very excited about. So, I've put my slides online. I will also show the link at the end again, and I'll share it on Twitter. So, if you want to then check the slides later, they will be available. So, who am I? My name is Anjo, and I currently work as a senior software engineer at Datadog. I've been a really big fan of Ruby since 2014 when I started to use it professionally. And I'm also a big fan of exploring language runtimes, the Ruby VM, the JVM, JRuby, etc. I also really like to spend time thinking about application performance and how we can make it better and also easier to do. And that's how I ended up working on making tools to uncover better performance insights. So basically looking at our applications in different ways and new ways to be able to learn more about them and what they are doing. So I work on the Datadog Ruby continuous profiler, which we'll be talking about today. But before that, if you hadn't heard about Datadog before, we provide cloud monitoring as a service. We have many things. But like for Ruby, we have like profiling, distributed tracing, security, errors, logs, and many other things for other programming languages as well. Here you have a pretty screenshot of like us showing tracing requests across multiple services and nice graphs for metrics and etc. A screenshot of the profiler where you can look at what the application was doing over like even like an hour or a day, so large amounts of time. And this is the profiling timeline view where you have like each line is a thread in your Ruby application, and you can see what that thread was doing a long time. So this is just a small bit of what we can provide. But today we're here to talk about the Ruby profiler. The Ruby profiler is part of the ddtrace gem. It's available on GitHub, so you can just get it, play with it. It's open source. And this actually means that you can see almost all of the work I've done at Datadog since I joined the company 3 years ago. It supports CRuby 2.5 and above, and actually, technically right now, on the current stable version, it's 2.3 and above, but we're going to release a new version where we're going to drop support, so 2.3 is hard. The profiler itself only really supports Linux and has like some hidden experimental macOS support. But if you want to play with it on macOS, my recommendation is run it inside Docker. It runs really well. But the gem itself, you can run it on Linux, macOS, etc. It's just the profiler has like some Linux-specific things that we still haven't ported to other OSs. The gem itself is built in a combination of Ruby plus C plus Rust, so that's pretty interesting. It produces data in this pprof format, which is like a standard format used by a bunch of profilers, so there's a lot of tools to use this data, even beyond Datadog. And the key thing is that it's built to be always on and in production, and this is the distinguishing feature of this profiler. An alternative title for this presentation could have been how to gather hundreds or thousands of profiling data points per second with low overhead, or how profile authors get to have fun pushing the Ruby VM right to its limits, and sometimes beyond. So there's already a bunch of great Ruby profilers out there, but the reason why we started building a new profiler at Datadog is that often they have like one or more of these caveats if you want to run them always on in production. They can add like overhead to your application, which is not great for production. They can also produce sometimes a lot of data. So if you are running that in production, you need to solve the problem of, am I going to store this like in a cloud instance? Where can I store it? What if I have containers? Where do I store this information? Do I upload it somewhere to S3? Some profilers also gather sensitive data. So for instance, here I'm thinking of like heap dumps and similar, where if you take a heap dump in production, you might have like database keys or like customer data in there. So you need to be careful in how you manage this. And some profilers only can track one type of data at a time, so CPU but not memory or vice versa. And the challenge that we had at Datadog was always on in production. So we wanted low overhead. For this, we use sampling as a technique. We wanted to efficiently manage data, so both in memory while we are gathering the data, as well as like when we upload it, so we manage this data automatically. Obviously, no sensitive data. And we wanted to track multiple kinds of profiling data simultaneously so you could see like the different things at the same time. A quick outline for this presentation. I'll be talking a bit about a few examples of profiling, the types of profiling data that we gather in the Ruby profiler, how we actually gather that data. Then I'll be talking about some of the challenges and workarounds that we needed to get this data from Ruby. And we do very, very weird things in the profiler, like don't do this at home. We're going to be talking about how we actually use Rust in the ddtrace gem for the profiler. And at the end, I'll talk a bit about why always on. What does that, like, why would you do that? Okay, so in practice, here's an actual real-world example from internal Datadog, actually. We actually use GitLab. So if you've never heard of GitLab, it's like like GitHub, but open source. So we have our own self-hosted instance of GitLab. And one of the people at Datadog that runs, and GitLab is also built in Ruby. And so someone from the team at Datadog that was managing GitLab reached out to me and said, like, OK, we have these requests that are failing with rack timeouts after 60 seconds. Can you help us? And then I went, OK, let's look at the profiler. And actually, when I looked at the profiler, I saw that actually most of the time was being spent on this method. Line 222, repository.rb in GitLab, match. And I'm like, OK, let's look at the code. Let's try to understand what's going on. So that's the magic line. But let me try to walk you through what this method is doing. So this is GitLab. So we're talking about the Git repository. What GitLab is doing is that it's trying to get all of the branch names and tag names from the repository. And it's trying to see which ones are a prefix of the other. So it's gathering all of the branch and tag names and separating them out with the ones that have a slash and the ones that don't have a slash. So if you have a branch named Anjo and another called Anjo slash something something, it's trying to find this. It's building a regular expression for all the names without a slash, and then it's matching like one to the other to find the ones that are prefixes. So this doesn't seem particularly bad. So I got to thinking, OK, what repository is this again? How can this be taking so long? How many branches and tags can be there that would take this long? And the answer is actually that this is a big Datadog front-end repo with more than 50,000 branches and 113,000 tags. And this was the reason. OK, if you're trying to match this many like regular expressions, it's going to take a while. And so I actually told this to my colleague. And actually, it turns out that we did not need all of those branches and tags. It's because we ran some synchronization thing. And the synchronization thing did not delete old branches and tags, and he did the cleanup, and now it's working again. So that's like one example of using the profiler to fix problems. The other one is actually from the gem itself. We have like some metrics that we publish, and one is class count, so how many classes are in your Ruby VM loaded. And so we check if the metric is available, because it might not be on some Ruby versions or JRuby. And if so, we publish it. And we had something like this where available, we check if the APIs existed in object space and if it included the key we wanted. And if so, we published it. But then when I look at the profile for this, I actually saw two big lines. So basically, we were taking we were taking double the time, because count objects, we were calling it 2 times, once to check if the key existed, and another one to check the value. So this is the kind of thing where when you wrote it, it seems like, oh, maybe it's OK. But it's not OK because it's an expensive thing. So actually, I fixed this one by caching this information. As a bonus, you can actually experiment with ddtrace locally without the Datadog account. So we have support for like custom exporting mechanisms. So here's like a 3-line exporter that just saves a profile to a file. And here's like a simple Fibonacci example. So you add ddtrace to your bundler. You run your app with ddtrace. You uncompress the profile. And here's another example. So we automatically compress the data. We don't even have the option for not compressed data. So this is one of the overhead limiting techniques. And then you can use any tool. This is using the Go tool. So Go also uses pprof and has a bunch of tools to visualize it. And here's how this very simple flame graph looks. OK, let's talk about profiling data and the types of profiling data that we can gather right now in this Ruby profiler. The first one is a classic, CPU time. So how much time was spent by code executing on CPU and where? So this roughly correlates to time spent by the Ruby VM actually running code. Although if you have code in a native extension and the native extension also does a lot of work, it will also be included. In particular, the key is that this does not include network, file access, waiting, etc., because these things do not use the CPU. And then we have wall time, which is how much real-world time was spent by what code in total. So the idea here is that, for instance, if you have a sleep does not need CPU, but actually takes time. So if you sleep for 10 seconds, you get 0 seconds of CPU and 10 seconds of wall time. This is the intuition. So it includes on CPU and off CPU. And off CPU can be network, waiting for the JVL, sleeping, locks, etc. And so the idea is that the wall time of a web request is the latency that your users will see. So sometimes if you're just looking at CPU time, you might not be looking at the right thing because maybe the request is slow because network, I/O, etc., not because of CPU. Another thing is allocations. So how many objects are getting created and where? If you create more objects, this means more work for the Ruby garbage collector. And as Koichi was showing off in his keynote yesterday, like the GC work impacts the whole application, not just the parts that are creating a lot of objects. So you need, this is definitely something to keep an eye on. And also we support having information for garbage collection. So how much time was spent by the garbage collector, and this is kind of the cost of too many objects. So if you think about it, like allocations and garbage collection are two sides of the same coin. Allocations are the cause of the problem, like where are you allocating all of these objects? And garbage collection is the result. How much is it's costing you? Like what's the impact on the application? So they pair really well together. Then we also have heap live objects. So the idea is that like track what objects are still alive after garbage collection. So the idea is that this is useful for tracking down object memory leaks, which are objects that are kept alive and should not. So this is specifically for Ruby objects and not for native extensions yet. So let's now go one level deeper and like talk about how we actually gather this information. So to control the overhead, this has been a big topic. Like all three profilers that we've talked at RubyKaigi this year use the same technique, sampling. So the idea is that if you try to record every method call, every object created, every event, this is very costly. So the challenge is that the profiling should not make the app slower, use more memory, etc. And so instead we use sampling. We don't record every event. Instead, we record periodically, and we try to create a statistically significant approximation of the app workload. And in practice, like you don't get a perfect picture because a perfect picture is very expensive, but you can get a really good picture for really low overhead with some work in the profiler. So this is what we're trying to get. Really good picture, low overhead. Okay, let's talk about details. CPU and wall time. So the idea for the Datadog Ruby profiler is that we have a background thread, and every 10 milliseconds, we record the state of other threads. This includes CPU time, wall time, the backtrace of what the thread was doing, a timestamp, the active web request, and some like the thread name, its state, some extra metadata. And we can build a few different views. So here on the left, you have a view which is the flame graph. And in the flame graph, like things that are wider spend more time. And so you can see this application was spending some time on different things. And you can see the backtrace represented of this application. So how we got to executing those things. For CPU time, there's actually no standard operating system API to get this information, but you can get it on most OSs. So like on Linux, for instance, there's like this like magic C code that you can throw at Linux, and you will get the amount of time that the thread actually spent on CPU. For wall time, we actually just record the time since the last sample. The timestamp that I said is used to build a different view. It's used to build a view that we call the timeline view, where the events are shown in order. So you might be familiar with this view from other tools, other profilers, where here we have one line per thread. So these are like a Puma web server running with 5 threads, and you can see like how it was active from left to right, what Puma was doing to serve this request. So this is why we need the timestamp. We also use the active web request. So the idea is that we already, for Datadog, we have a bunch of instrumentation for what's the current active endpoint and distributed trace that's flowing through your application. So we actually read this information from the profiler. And the idea is that we can then filter the profile to like just one single request. So I want to profile just one request, even if I have data for all of them, or even just a single endpoint. So you can see like, can you show me a profile for this endpoint for the last 4 hours, which we call endpoint profiling. And this is especially useful for multi-threaded apps because on a single-threaded app like Unicorn, you can just like, OK, one at a time, you can just look at it. But if you have something like Puma, you can have a lot of information at the same time. So this is helpful to help you filter. And it looks something like this, and I can zoom in a bit. So here is like the one Puma thread that was working on this request. And you can actually see it spent some time on CPU, the blue part, then spent some time on I/O, the purple part, and then it had like some sleeps in there, which is the gray part. And like so in total, it spent a bunch of time. But we can see what this request was doing in particular. You might also be wondering, I've told you, from a background thread, every 10 milliseconds we record the state. But what about the global VM lock, the JVL? Like, does the profiler need to wait for its turn to execute? What if the JVL takes longer than 10 milliseconds? And here the answer is that we actually have this background thread that is built in C and runs in the background without the JVL. And it interrupts the active thread from Ruby that has the JVL. So we see what's the currently active thread, and then we interrupt it with what's called the Unix signal. And then in that thread, we use like a VM API called RB postpone job trigger to ask Ruby to like take a sample. So this is how we tackle this one. You might also be wondering, OK, what if 10 milliseconds is still too much overhead? I don't want this to impact my application. And the answer is that we actually measure how much the profiler spends sampling, and we will sleep for longer to reduce the overhead if needed. So if your application is suddenly very, very busy or on like a cloud host that has many processes and the processes are being impacted, so we will reduce the amount of time that the profiler spends working to compensate for this. Let's talk about garbage collection. So what we do for garbage collection is that there's a trace point for the GC enter and GC exit events. And if you've never heard of these events in trace points, it's because they are only available to native extensions. So you cannot create a Ruby level trace point with these events. You can only create like a native code event. And the idea is that Ruby actually splits the GC work into many steps because the Ruby GC is incremental. So we need to be careful because these trace points can get called for every one of these steps. So I've seen it being called like hundreds or even thousands of times per second in micro benchmarks, but like it can get very high. So you need to do some work to batch the work that you do so that you keep the overhead low. The other interesting key is that like Ruby does GC in whatever thread was active, but actually we create like a virtual thread to centralize it, so we kind of show it in a different line. And you can see on this application how there was like some GC active all the time, and then suddenly there was like a major GC, and you can see the impact it had on the application because the application kind of stopped running, and that was like a big pause on the application because the major GC was running. And yeah, let's talk about allocations. Allocations, another trace point, new object. And again, it's only available to native extensions. And then every n objects that are allocated in your application, the idea is that we record the backtrace, the class, and the active web request, and some extra things, and we can build something like the table you see there of how many of each instance were allocated. And you might be wondering, I said like every n objects. So what's a good value for n that keeps overhead low? And the answer is trick question. There is no good value for n. The actual good answer is that you need to adjust n based on what the application is doing and the current overhead. So the idea is that like if you have a very well-tuned application that allocates very little, if you allocate like 10 objects per request, then we will need to want to have like an n number very close to 1, because if you set it to 1,000, then you will never see any information. But so otherwise, too little data. But if you are allocating a lot of objects, then n needs to be a very large number, because otherwise the profiler would impact your application a lot. So this is the kind of decision where we have to take all the time, which is how can we gather this information with low overhead? And then we have heap live, so the thing to detect memory leaks. The idea is that we reuse the allocation's trace point, and then every m objects that the allocation profiler chose, we record the backtrace, the object ID, and some extra metadata. And then what we do is that every minute, we use ID to ref to check, is this object still alive? And then if it is, we include this object in a profile. If it's not, we clean it up. And so the trick here is that if you have like a tool that can do like a diff between two profiles, you see, okay, what were the objects active 4 hours ago? What are the objects active now? And you can see like, oh, we have a lot more instances of this in memory that are not being cleaned up. This has a very like catch, which is like, if you have like a very small amount of large objects, so if you like every 10,000 objects that are very small, you allocate one that's very big, we might not be able to track it, but we have some ideas for it. So this is definitely something we want to improve on. Let's go one level deeper and talk a bit about also some of the challenges and workarounds that we had while building this profiler. So TLDR is that profiling stretches the VM to its limits to get all of this data with low overhead. And there's a few more things that we even wish we could do, and that we hope to have some of those conversations with so many profiler folks here. And actually, I had a bunch more slides here, and then I decided I need to cut them because I didn't have time. So I actually created like a doc where I'm tracking some of these things, and I would love to chat about them. So one of the things is like the lowering the overhead of allocations and heap profiling. So the Ruby, if you look at the Ruby VM code, the object allocation code has both a fast and a slow path. It basically goes, if something, something, fast allocation, else slow allocation. And most of the times, you get the fast allocation. But if you create a new object trace point, then if something, something is false, and you always get a slow allocation. Actually, obviously, fast and slow here are a bit relative. Like, and on most applications we've tested, this impact is not that big, but you can definitely measure it, especially on micro benchmarks. So definitely, this is something that we would like to be able to improve and make it so that we can profile and still use the fast path. The other thing is rectors. So right now, there's this weird behavior in the VM where if a rector, like you create a rector, the rector does a bunch of things, and then at some point, the rector dies. Then Ruby will garbage collect the rector, but when it does, it disables the active trace points that you might have. And this means that like some of the features of the profiler stop collecting data when you use rectors. And there's actually like an open bug for this, and even a PR, and this one is one that I would love to push along. The other one that is very interesting is like sampling from the signal handler. So this is a very like specific detail, but if you are able to send a signal to a Ruby thread and get a stack trace from the signal handler directly, and this is something that was discussed yesterday as well, this enables very highly accurate CPU profiling, and like Go and even other runtimes use this very successfully, such as Java. The thing that is that like in some cases, it's not actually guaranteed in Ruby that updating the frame pointer is atomic. And so some compilers might do this wrong. And so actually, because we are concerned about like not impacting applications, we actually don't use this feature, but this would be really nice if it was possible. And I think this would be usable for many other profilers, including those that work from inside the Linux kernel. So I removed a bunch of slides, and instead I added like one big thanks for the community. So a lot of things have been fixed and like improved in Ruby recently that make profilers' lives infinitely better. I forgot people, I'm sure, but thank you so far. So yes, let's finally talk a bit about like using Rust in a gem, because this is not a very common thing, and the ddtrace gem has been downloaded. Well, download numbers are always like an approximation, but like been downloaded more than 17,000 times. And we use Rust in a gem. So I'm not sure, but we are definitely one of the biggest users of Rust in gems, I would suspect. So how do we do this? Actually, the Ruby profiler uses Rust to implement data storage and serialization. So a bunch of these things are very efficiently implemented using Rust and very safely, which is good. And what we do is that we actually have a second gem, which is called the libdatadog gem. It's also open source, also up on GitHub. And the idea is that we distribute as a binary gem on Ruby gems, but it's the same thing you get if you build it from source. And the key thing is that this allows us to install it without people having a Rust compiler around, or even like a specific version of Rust, because we are all the time wanting to use new Rust features. Rust is a language that's evolving very fast, and so often you want to use new features. So this allows us to just use the latest features, and nobody has to know that they need to install Rust and whatever. It's just magic. So the full solution is that we use a mix of C and Rust, which I believe is kind of what YJIT does as well. Like there's some C, and then like most of YJIT is in Rust. And so when you install the ddtrace gem, we build the native C extension from source, like so many other Ruby extensions. And then we pull in the libdatadog gem as a binary, and then we link both. And then, so we have the Ruby-specific part in C, and then we can keep one Rust native component that is used across multiple Ruby versions, although we need binaries for different platforms that we support. OK, finally, let me talk a bit about like why always-on production profiling is something that you should care about. One thing is that it allows you to investigate problems. So if you are running the profiler always on, when you get paged and you have a problem, you can immediately start asking the questions like, what changed? What's causing issues now? Like, what was the app doing like 4 hours ago when it was OK, but not now? So what's using so much, like there's a CPU spike. What's using so much CPU suddenly? What changed? Why was this one request that someone like opened a ticket for like slower than the other requests? And especially things that are hard to reproduce in staging. Production is very different. It has like more customers, weird customers, old data, old like whatever. Staging is usually like pretty. And production is hard. And it's things like the unknown unknown. So this is the things that you might not even know about. You might have instrumentation for a bunch of things, but did you know that this database driver creates a background thread, and this background thread is doing a lot of something. So this is the kind of thing that a profiler allows you to see. Another one is reducing latency. So obviously, if you optimize your app, usually you can make your users happier. You need to be careful, though. So don't just optimize whatever. You need to find which parts of the application are the most important to optimize. It might not even be in Ruby. And this is like a common caveat. You think you optimize your Ruby code and you don't improve your users a lot because there's a big impact on JavaScript or on the database. And even something like profile guided optimization. I've been using Go as an example a lot, and I use Go again. Like recently, Go added like profile guided optimization. So actually, you can download a profile from production and give this profile to the Go compiler, and Go will use that to make better decisions to how it optimizes stuff. So maybe ideas for YJIT, being able to supply a profile to make better decisions. Also, obviously, reduce costs. So if you find like a bunch of low-hanging fruit, you find the biggest resource consumers on your application, and you reduce them, obviously, many times that's going to be, you'll be able to use less instances in the cloud, so that's less money, that's good. And finally, there's a reason that doesn't get talked very often that I really, really like to, that's my favorite reason for using a profiler. It's the learning and discovering. So you come into a team, you don't know what your service that you're working on is doing. It's actually very interesting to see like the service using a profiler because you can tell like what does it spend its time, like its whole day is doing. So you can find the important code paths, the really impactful things. And on the other hand, if you've been working on a service for like 2 years and you have a really good mental model of it, and you compare your mental model with what the profiler shows, if they match, no matter. But if they don't match, you will have the opportunity to learn something. And often you get surprised. You might be wondering, oh, I thought this was spending a lot of time doing this, but it's actually spending a lot of time in logging. True story. Or maybe you thought you had removed some code or a feature flag, and you see it right there consuming time, and you're like, oh, we had removed this. I thought we had removed this. So this is the kind of thing where if you are experienced and you compare with what you have, it's very successful. So that's what I had. Thank you. Let's make Ruby apps even faster together. I'm Ivo. There's the link to the slides and the other things that I would like to discuss. And yeah, please email me, please talk to me. And Datadog is hiring, and I thank them for paying for my trip here. Thank you.